can't seem to find any kind of eraser. Chalk for that matter. Ah, yes. I think some eraser. Okay, so in the last lecture we talked about maximally symmetric spaces, and we covered Minkowski in a bunch of different coordinates and also did the Penrose diagram. And what the plan is now today and tomorrow to just do the same for deSitter and anti-deSitter spacetimes, because these are the three maximally symmetric spacetimes. And once we do that, as I'm sure you know, that's sort of a basis for considering all other spacetimes in a sets a kind of basis in the following sense that any spacetime will be asymptotically one of these three. The global properties being very different between three of them, and so let's just get down to it. So today we want to talk about deSitter spacetime. So let me start by writing. I think this is lecture 7. And today is 3rd of March. Okay, so we want to discuss deSitter spacetime. And the idea of how to describe it is quite simple. The thing that we know best is flat spacetime. And as we did, which is Minkowski in Lorentzian signature, and we discussed it last time. And let's just assume we know that very well. How do we find other symmetric spacetimes? Well, we steal the idea from Euclidean signature geometry, where if we want to find a sphere, which is a very symmetric space, then we just embed it in a space-time or in another space of one higher dimension. And so, as you know, if I do in R b plus 1, if I write summation xi squared equals R squared, then I get a d-dimensional sphere. And the nice thing is that the sphere inherits its symmetries from the space in which it's embedded. And basically the way that works is that if the space in which I'm embedding my manifold has some symmetries, and if the embedding equation, which here is this one, also has those symmetries, then the embedded space of one lower dimension will have the same symmetries. It has to, because the higher dimensional space had those symmetries, isometries, and the equation respected them. So you can't have lost anything. So how does it work here? Well, RB plus 1 has RD plus 1 as D plus 1 translations, and D plus 1 into D over 2 rotations. So this equation actually respects the rotation part of it, not the translations, because it's based on x squared. So those go, but you have this many rotations in the higher dimensions, and all of them must be symmetries of the D sphere. While if the D sphere was not a sphere but a flat space, then it would have only d minus 1 over 2, but actually it has a somewhat larger set of symmetries. So this is the idea, and now we can apply it to an embedding space. So when I say embedding space, I mean the higher dimensional one, and then I'll embed something of one lower, which will have one lower dimension. So this is an example. So now we consider D plus 1 dimensional Minkowski spacetime, and we write its metric as minus dx0 squared plus dxi squared. So the only thing we've changed is to make one of the coordinates time-like. And now what we want to do is to embed. So embedding is done by a constraint equation. So the constraint will be minus x0 squared plus xi squared equals constant. So as you can see, this has the same signature as that, and so the symmetries of that are also symmetries of this. Now here we find something a little new already, which is that we have to pick the sign of this constant. Now let's recall what happened with the sphere. If for some reason we chose the right side thing not to be r squared but minus r squared, what would happen? We wouldn't get any solutions in real geometry. So it's a completely different space with r squared positive and negative. Okay, so here also it will be different with this right hand side positive or negative. So first we are going to discuss the case where this is positive. Then I'll briefly remark what happens if it's negative. So this should have symmetries O, D, comma 1, because those were the symmetries of Minkowski spacetime. Okay. Now there's an interesting fact, which is that if I have one way to solve this is to eliminate one of the coordinates in terms of the others. It's not a very useful way in practice, but certainly you can do it. And so we just solve by picking xd, and I just write it as plus or minus the square root of L squared plus x0 squared minus xi squared summed from 1 to only b minus 1. So I can do this, and you see that in this equation there is still a subgroup of symmetries which transform this Lorentzian thing, because this thing is just Minkowski spacetime by itself of one lower dimension. So with these, this quadratic form is invariant, already we know, under SO d minus 1, comma 1, and we also know that the symmetry acts linearly. So it's just the rotation of in a quadratic form. To preserve a quadratic form, you just need to make a linear transformation on these, and it will be preserved. Those are the Lorentz transformations, and we know that they are linear. So we have I won't put S, just OD minus 1, comma 1. So on one hand we have this many symmetries, on the other hand we have this many which act linearly. Okay. Now what's the difference between the number of these and the number of these? Well, these are d plus 1 by 2, and these are d minus 1 by 2, and so the difference is d. So we conclude that therefore there are d minus 1 by 2 linear symmetries. This is in this given choice of coordinates, and plus d non-linear ones. We can also see why they are non-linear, because they are the ones which in the original quadratic form would have mixed xd with the remaining coordinates. Okay, but now we singled out xd and solved it as a square root. So the transformations which mix xd with the other coordinates are no longer visible. We are actually going to eliminate xd. This eliminates xd. And we have to eliminate one coordinate if we want to get a d-dimensional space. So this solves the constraint, but then it makes these symmetries act non-linearly. And in fact, this leads to a very classic result, which is also has its counterpart in Riemannian geometry, which is that the space, so this space-time is the coset OD1 over O D minus 1 is the coset space. And what that means is OD1 will be a group manifold. This is the group manifold of that Lorentz group. So there's some manifold, in general it's curved and all that. It has a natural submanifold OD minus 1 comma 1, because for any Lie group, if I have a subgroup, then the manifold of that is a submanifold of the Lie group. However, what happens now is that, okay, so what this coset means is that within this manifold, I identify all sets of points from where I can go from one to another by only using OD minus 1 comma 1. Okay, so that's the coset. What's the dimension of this space? The dimension is the difference between dimension of the numerator and denominator, because after I make enough identifications, my space reduces in dimension, and actually the dimension at the end is D, precisely the difference, this difference that I already calculated. It's also true, for example, that a sphere is something like OD over OD minus 1, not something like, it is, yeah, question?
Is it always true that the coset space always acts non-linearly?
The coset space doesn't act, so the group acts.
Group acts.
Yeah, so what happens here is when I have a coset G by H, then the denominator H acts linearly, and everything in G which is not in H acts non-linearly on the space. That is a general statement about coset spaces. Good. Okay. So anyway, so this space-time goes by the name of deSitter, named after his discoverer, Wilhelm deSitter, who was actually looking for solutions to Einstein's equations. Here we haven't started talking about Einstein's equations, though we will fairly soon. But I think you already know that it solves the equation R nu minus half G mu R. Let me just check my conventions. I might not be able to find the conventions right at this minute, but it is, I've written it somewhere. So when I get to talk about, yeah, these are the conventions. Yeah.
So I just have some doubt regarding the coset thing which you mentioned.
Yeah.
So if I'm clear, just could you just show the XD? So the coset thing is saying that by any transformation under OD minus 1, the part under the square root changes, but that x naught square minus that remains invariant.
Yeah.
So for any such transformation which leaves that invariant, XD is identified. Basically, XD gives the same value.
Yes.
So that's why all those points which are related by OD minus 1 give the same value. That's what we are saying by that.
Well, that's certainly a true statement. I'm simply saying that if you want to know the action of this denominator on the coordinates of the embedding space, it's linear. That's all. So and it can be linear only because it leaves XD invariant.
Yeah.
See, these are redundant. I mean, if you keep XD and all of these, then it's a redundant set of coordinates. That's why we have this equation in the first place. But the OD minus 1 comma 1 only mixes the D minus 1 subset. So this is a d-dimensional set of coordinates. So it's a correct dimensionality of the final space. But it's not guaranteed that you can describe the final space by a quadratic form. It's not a flat space, right? But this part of the transformation just acts on these which do form a quadratic form, and therefore these are realized linearly. There are lots of discussions on coset spaces in differential geometry. You can, and in Lie groups, so you can look those up. Okay. Now, so this is deSitter, and it solves, as I said, this equation and we'll do that in a minute, but right now we need to still find coordinates. What we've only done is to eliminate xd. Now you could think of these, okay, maybe I should, since you asked this question about nonlinear, let me explain one more thing. You see, what was the metric of the original embedding space? It had a minus the original space of d plus 1 dimensions. This comment might help you understand this linear versus non-linear story. It had ds square equals minus dx0 squared plus dxi squared. Now I'm going to separate out the d minus 1 of them plus dxd squared. Is the same as I wrote at the beginning, but I separated out dxd. Now you see, with this elimination, that elimination formula, these are going to be the independent coordinates. This is no longer an independent coordinate. So here I have to differentiate that, take its first differential. So I have to replace it by some complicated function, and then there will be some, it will give me some dx0 squared plus something with some coefficients. Right? It has to do that. It's just going to be some quadratic form in the remaining dx's. Okay. Now, because the linear transformations keep xd fixed, they only have to keep this part fixed, and therefore they can be linear. That's sort of, so the transformations which keep xd fixed act linearly on these. Okay? And they'll also do that inside here, but we don't have to worry because we know they keep xd fixed. But the ones which don't keep xd fixed have to mix these x0 and xi here with things there, and these things come with functions. So they're bound to be nonlinear. The simplest example, non-trivial example, I think, is the two-sphere, which can be written as O3 over O2. Yeah, you can just work out in that case. Yeah, question?
Sir, we can eliminate any of the coordinates.
Yes, absolutely.
But then if we choose to eliminate x naught, then the space that we have would not have any minus sign signature, then it's a...
Yeah, actually that is correct. That is correct. I'm not sure what the answer that is. So, if I chose to, no, that's not correct. That's not correct. In fact, you can eliminate x naught. It doesn't mean the space won't have any minus signature, because all I find here is that then x naught will be some combination of xi and else. But I still, in the metric, I still have minus dx naught squared. So I have to now solve x naught in terms of the other stuff and put it here. And I think I'll still get at least one, exactly one negative eigenvalue. It will be one of the others. Or it may be a combination of the others, yeah?
The only thing that will change is the modding, what we are doing. It will be OD, just OD, right?
Yeah, if you solve for x0, it certainly looks like OD is linearly realized, and yeah, why not actually? That can be the case. Yeah.
So, I mean, I don't really see how you are saying from the linear versus non-linear action that the space is a coset.
No, that doesn't immediately follow from that. I'm just giving a plausibility that if you think of a coset, cosets have this property that the denominator always acts linearly, but I didn't prove that it's a coset space.
And also this coset representation does not, it's just locally the same as this deSitter, right? Does it also have the same global structure?
I think it has the same global structure as global deSitter. Should have. This is not just a local statement in general. deSitter itself has local, I mean, there are patches, we'll be discussing different coordinates, but I think the coset description should give the whole of deSitter. Just as it in Riemannian case, it gives the whole sphere. Okay. So now let's look for some more natural coordinates. So it's a nice exercise that you can work out the details of this metric and stare at it and see what you can learn from it. We'll actually write down several metrics on deSitter, and Probably some of them actually might actually be the same as this in some other disguise. Okay, so the sort of first coordinates we would like to discuss are called global coordinates. We cover all of deSitter, and the idea is to parameterize x0. Okay, so the constant on the right side, did I call it L squared? It's supposed to be L squared.
Yeah.
I think I did. Okay. So then I will parameterize x0 as L sine hyperbolic t. Since sine hyperbolic takes both signs, it covers minus to plus infinity. So that's fine. And then the remaining xi, I will put an L, I'll put a cos hyperbolic of t, and I'll put a unit vector ni, which has the property that it's constrained to square to 1 unit vector. So this is a vector on, so unit vector on SD, I believe, yes. No, sorry, it's a unit vector in d dimensions that describes SD minus 1. You just have a unit vector in d dimensions, so all it can do is rotate. When you take the points it sweeps out by rotating, you get a sphere of unit radius in d dimensions, and that's SD minus 1. Okay. Important to realize that although cosh is always positive, this n can point in all directions, so we are not losing any points of the space by this parameterization. You can invert it and it's quite straightforward. Okay, now you insert, okay, one consequence of this constraint is that ni, dni, these are all understood to be summed over I. This is 0. Just if I take the infinitesimal of this, I get this. This makes certain cross terms cancel out when I start inserting this in the metric, and I end up with ds squared is equal to an overall factor of L squared times minus dt squared plus cosh squared t d omega d minus 1 squared. This object is actually the same as dni. Okay, in this language is the metric on a space of decomponent vectors, but which satisfy a constraint. But I can, since this is just, I can treat it as the abstract object d omega d minus 1, which is just the metric on a unit sphere, and I can describe it with any way I want, typically with angles, which in which case I don't need a constraint. This is a constraint way of describing it. Okay. So these are called global coordinates, and several things can be said about this. So first of all, it's time dependent, so it's really a cosmology. Generally we refer to time dependent metrics as cosmologies. And in fact it's of FRW form. So it's homogeneous and isotropic with scale factor A of t just being cosh of t. So it describes a universe that as time evolves from the far past, it's contracting because cosh is has a minimum value of 1 at t equals 0. So if t is negative, it's contracting until t equals 0, and then after that it's expanding again. So people generally draw this kind of shape with the cross sections being at fixed time. This is t, and these cross sections are the d minus 1 sphere. So that's the sort of picture we get. Okay, now at this point I can tell you what would happen if we had started with our constraint equation not as minus dx0 squared plus dxi squared is L squared, but supposing we put minus L squared instead, then this would have been a plus. Okay, and there's that teaches us a general rule which is worth remembering. In a constraint equation, let's I might be closer on the other side. But let's just write it here. So minus x0 squared plus xi squared equals minus L squared leads to a Euclidean signature metric. And this is a useful general rule to keep in mind because we'll be using this rule again in anti-deSitter. If I have a constraint with a certain sign on the right side, that constraint removes a coordinate from the left side which is of the same sign. So if I put minus here, then it removes this, not necessarily this particular coordinate, but it removes a coordinate of negative signature, leaving behind a metric of Euclidean signature. If on the other hand this is plus, then it removes one of these. We also saw how to do that effectively. Okay, good. We can write the metric of ds3 explicitly. For example, it's just minus dt squared plus sine squared, plus d theta squared plus sine squared theta d phi squared, this whole thing multiplied by cos squared t. So this is just an example. Yes.
One small doubt.
Yes.
Those global coordinates, we put it in which metric to get ds squared equal to h squared to that?
We put the global coordinates. I see. Okay, I should explain that better. Thank you. So the point is that these are rigged up to solve the constraint. Okay, so this choice, these are still redundant, so you have to put them in the embedding space metric. In the Minkowski metric. But the point is that they automatically solve the constraint. So if you see on the left side, I have d plus 1 coordinates. On the right side, I only have d coordinates, ni and t. Of course, it looks like d plus 1 because there are d of these and 1 t, but n is constraint. So the constraint that I had imposed in Minkowski spacetime just becomes the constraint on n. So the important point about this choice is that by virtue of a constraint on n, this satisfies L squared. So it solves the constraint. Yeah.
This metric which we get in the deSitter metric.
Yeah, the metric we got is the deSitter metric in independent coordinates. Now there's no more any constraint. So for example, for ds3, there's one angle, two angles, that's a two sphere and one time, and the two sphere is shrinking and expanding. In ds4, there'll be three angles and one time, like that.
So suppose we have any metric,
Yeah.
and we impose a constraint on the coordinates, we can get a different metric.
Of course, that's the whole point, that deSitter spacetime is different from Minkowski, right?
And those two metrics will have different curvatures.
Everything different. I mean, it's the basic example is the sphere in flat space, right? Supposing I have x squared plus x, y and z, and I embed x squared plus y squared plus z squared equals 1, I get a two sphere. So first of all, the original space was 3D, but now I've got a two sphere. Secondly, the original space was flat, but now I've got a curved surface. It's exactly the same idea. It's a totally different space time from the Minkowski one. It's just the embedding trick was the way to get it. I'm not even sure if that's what deSitter used, but it's a very standard way to get it. And once we have this embedding, we can try to solve it in all possible clever ways and get all possible interesting coordinate systems. And in physics, it often happens that different coordinate systems are useful for different problems. Okay. Now, in fact, So this is just an example. So in fact, there's a non-vanishing, so it is a curved space-time. And so it has a Riemann tensor, which is in general non-zero. This is unlike Minkowski. Now we could calculate it just starting from this metric, and it's a nice exercise to do once. But there's a simpler thing we could do. So simple way to calculate it. Would be to instead calculate the Ricci scalar from the metric. So if you are familiar with the formulae which give you Riemann tensor from a metric, which are very standard, I might have written it down in the first lecture. The one for the Ricci scalar is the simplest because it's just one thing. So you can just calculate it, and you actually find that this is d into d minus 1 by L squared. So this is an exercise, and now there's a theorem. I'm not sure whether I spent time talking about it or not. That for a maximally symmetric space, it's not very hard to prove. It's proved in the elementary books like Carroll and so on. The Riemann tensor is fully determined in terms of the Ricci tensor. That's the only thing you need to know. Basically, what you have to argue is that good. So this is, I believe, 1 over d minus 1 g mu rho g mu sigma. Basically, you have to argue that the tensor, the Riemann tensor, is just given in terms of the metric. Then this is the only bilinear form, the only form in the metric which can give you an object with the same symmetries as the Riemann tensor.
L square also.
Yeah, this is general, and here there is the Ricci scalar. I forgot to put that. Okay, now if I put this, so this is general. Any maximally symmetric space has a Riemann tensor R upon where this is the Ricci scalar and rest. Okay, and so it's equal to 1 by L squared. Same contraction for deSitter. And we see that now we finally see the interpretation of the L on the right side of that constraint equation. It's the inverse curvature basically of the space. It sets the inverse scale of the curvature, and therefore we call L the deSitter radius. It's not literally a radius because deSitter is not a sphere, but it has the same effect. If you look at the formulae for a sphere, you will get the same, in fact you will get the same Ricci scalar, and you will get the same formula for the Riemann tensor like this, but then in that case L will be the radius, actual radius of the sphere.
Why is it square? The power of L is 2.
Power of L is 2, why where? In R?
In R, yes.
It has G inverses and G's, and let's see. Good question. We should be able to figure this out quickly.
We can do that by dimensional analysis, right?
We can do it by dimensional analysis, that is correct. I think what we are doing actually is getting a dimensionless version of the Riemann tensor. Am I right? Yeah, because the way I have defined the metric, it has L in front of it, right? I think I wrote the metric as L times some stuff. So here you have two metrics, both have L. This cancels all the dimension. Okay, and Um, yes. So with this and this, you also get the Ricci tensor. We need that as well, and that is d minus 1 only by L square. G mu nu, that's all it can be. Ricci tensor has no choice but to be just proportional to the metric. Okay. Now the Einstein equation with cosmological constant is R mu nu minus half G mu nu, and then there's a term what? D minus 1, D minus 2. Sorry, I think I forgot to write something in my notes. Yeah. So 1 over D minus 1, D minus 2 lambda G mu nu is equal to 0. This is the general Einstein equation in general dimensions. Or there's a 2 also, maybe. 2 here. So only in 4 dimensions, this is 1/3. I think that's right. Is that right? I have it written somewhere else. Anyway, let's try to see if this works. So let's assume now I might have got the 2 in the wrong place. I think 2 might have been in the denominator. No, I think 2 is right. So now let's calculate. Okay, so let me assume this is the Einstein equation and we'll verify that. Let's just calculate this from 2 formulas. R mu nu is that and R is just dd minus 1 over L square. So if I calculate all this, I get minus d minus 1. Sorry, I think I got this thing wrong. We'll fix it in a minute. D minus 1, D minus 2 upon L square G mu nu. Okay, and I think this is just this. And this, 2.
In the denominator.
In the Ricci scalar.
In the Ricci scalar, there's a 2? No, at least not in my notes.
No, in the smell of lambda it is 1 by 2 L square. D to D.
So anyway, what I'm trying to claim is that lambda is d minus 1, d minus 2 upon L square. Is this upon 2L squared? And this also has a 2. So the Einstein equation is just that. I don't know why I got confused thinking it has some coefficients, but it's a convention, of course. But in that convention, lambda is this. And of course, it's greater than 0. And it goes to 0 only if L is infinite. And from our experience, we know that if L is infinite, that means the radius of curvature of some space is infinite, then the space becomes flatter and flatter in that limit. Good. Just check if anyone, please check if you think there are some factors of 2, let me know.
No, fine.
Huh?
It's fine.
It's fine? Good. Okay. Now, one thing we see is since the metric is time dependent in global coordinates, so del by del t is definitely not a killing vector. mentioned once when we studied killing vectors that if you can see a metric which is independent of some coordinate, then d by d that coordinate is automatically a killing vector, and that's very good because then you can ask the question that, okay, that coordinate, is it time-like or space-like? Then you'll know whether your killing vector is time-like or space-like. Right now, we only know that this is not a killing vector, but this doesn't tell us whether there is a time-like killing vector in the space-time or other killing vectors, and there must be lots of killing vectors because it's a maximally symmetric space-time. It has to actually have d plus 1 by 2 of them. So it's quite a struggle to find all of them and even to determine whether there is one that's time-like, and if so, is it time-like everywhere? It might be time-like and it might curve around to become something else. So the best bet is to find another system of coordinates in which we can see the existence of certain killing vectors. And what we'll find now, what we'll study now are the so-called static coordinates, in which indeed there is a time-like killing vector which we can see, but unfortunately those coordinates only cover a patch of deSitter space-time. So it means that there really isn't a time-like killing vector that is everywhere time-like in the space-time, but in some region it is. But let's do it. So this is second set of coordinates. They're called static coordinates. And for this, again we do something where we single out one of the coordinates arbitrarily. So what we do is we solve the constraint by the following statement. We divide x mu, this is capital X I'll try to always use for the embedding space. So it's one higher dimensional than the deSitter space-time. So x0, then I'll pick xd and xa, where a is 1 up to d minus 1. So I'll pick all of these in a way that solves the constraint, but not the way that I did before. So I'll start by saying that xa is r times na, where n, a, and a is 1. So this is a unit vector, but in d minus 1 dimension, so it describes a d minus 2 sphere. So you can anticipate that in its final form, the metric will have a d omega d minus 2 rather than d minus 1. Okay. Where r, so this, we just write it this way, and if we put this into the constraint, then we immediately see that these two have to take the values square root of L squared minus R squared sine hyperbolic of t and square root of L squared minus R squared cos hyperbolic of t. So let's see how this works. So then we have for minus x0 squared, we have L squared minus R squared sine hyperbolic squared of t. Then we have plus this one squared, so L squared minus R squared cos hyperbolic squared of t. And then for these, we have plus R squared. Okay, and you can see what's happening here. Cos squared minus sin squared is 1, so we get L squared minus R squared plus R squared, so that's equal to L squared as desired. Good. Notice that the x0 and xd look a bit like Rindler coordinates. They have this characteristic sine and cos hyperbolic, so they are like what an accelerated observer sees. There's another thing, which is that there's now a restriction that r must be less than L. Otherwise, if it becomes L or greater than L, then the coordinates either vanish identically or they turn imaginary, and that's not acceptable. So if we try to put that restriction in, it amounts to saying that xd, this implies, first of all, once you have this, you can see that xd is positive. So, of course, the original deSitter spacetime had a possibility of negative xd, but this doesn't. So, xd is just stuck to be positive. That's one constraint. But there's also a constraint which is that sine hyperbolic, so the existence of cos t implies this. Then also sine hyperbolic is always less than cos hyperbolic. In fact, mod is also less. So, this tells us that x0 is less than xd. Mod of x0 is less than xd. And this is a wedge. And if we want to, we're still in the embedding space and we'll come down to the actual deSitter. But within the embedding space, if I just take this to be xd and this to be x0, then the space which satisfies these two conditions is this one. Xd is always greater than 0, and x0 cannot get too large unless you are quite far out. So this is so that it's always bounded by this. And x0 is, because of this mod sign, it is allowed to be negative, but still its magnitude is bounded by this line. Okay. Now let's write the metric. So there are always two steps in defining a coordinate system. First you choose the coordinates which solve the constraint, and then you insert that choice of coordinates into your flat Minkowski metric. Since the constraint is automatically satisfied, at the end you will find a metric for one lower dimensional space-time. And here you very easily find that ds squared is minus L squared minus R squared dt squared. You can just see that from the change of coordinates, plus 1 over L squared minus R squared d R squared over this dr squared. This comes from only minus dx0 squared plus dx d squared, but there are more terms. You get also a dr squared, this comes from that sphere, plus r squared d omega d minus 2 squared. This is the sphere part, or this is the planar part. This is just a Euclidean d minus 1 space. Now this term and this term actually combine, so it's minus L squared minus R squared dt squared plus, when this combines with that, the R squared is replaced by L squared. So we get L squared over L squared minus R squared d R squared, and then we get R squared d omega d minus 2 squared, and that's the final answer. So these are this is the metric in static coordinates, and you can see that it lives up to its name because the coefficients of the metric don't depend on t anymore. So d by dt is a Killing vector now, and it's of course time-like. Good. Okay. Now there's a nice thing we can already see in this. We can see some features, physical or geometrical features. Sure, I said that it should be defined for r less than L, but actually it's a sensible metric also for r greater than L. However, it's not sensible when r is equal to L because the time disappears and the space thing blows up. Okay, but for r greater than L, this changes sign, this changes sign, and so now this is the time-like coordinate and this becomes a space-like coordinate. So can be extended, can be, or I won't say extended, is well defined also at r greater than L, but dt and dr exchange their roles. I don't mean that they are symmetric, I mean that the one which is time becomes a space and vice versa.
But in that case, will there be a time-like killing vector? Because
Certainly not this one, but this one will become a space-like killing vector. But note something else. I have not told you what are all. You see, we are asking me question like, will there be? I have not exhaustively studied anything like what will there be as killing vectors. There will always be d into d plus 1 by 2. So the fact that d by dt is not a time-like killing vector doesn't mean there isn't another one. But what is true is that d by dt certainly changes from being time-like to being space-like on the other side. But you can't continuously, you don't have one metric which interpolates from this r less than L to r greater than L, because at r equals L, this is singular. Now, there's a standard fix for this which most people know in the context of black holes, but this is a much simpler space-time. But there's a similar fix which works very nicely here, which is to define Eddington-Finkelstein coordinates. I really don't know the history whether it was first understood. In this case, probably not. I think deSitter horizon was something, I don't know, maybe something that people started worrying about later. In any case, as you know, after the discovery of black holes, Schwarzschild black hole in 1905, there was a period of couple of decades when not very much happened in the field at all. So, but that is the period, I think, in which deSitter discovered his metric also. Yeah.
So for r greater than L, the x0 and xt become imaginary.
Yeah, but we don't care about those anymore. So it's not, once we reach this metric, so this metric we have derived from the embedding space only for r less than L. After this, x0 and all those capital X's have no more any use for us because we are already in the physical space. All we are saying now is that this metric in these coordinates makes sense beyond the domain where we defined it.
But it may not be another part of that.
Yeah, it's not another. Yeah, it's not another part of that actually. And also, so it has two problems. Well, it is not a part of that. We don't need to care about that. In GR, we often find a space-time which exists in some region of space and time, and then we see if we can extend it. So in the next section of this course on causality, we'll be talking a lot about extendable and inextendable space-times and so on. So we should feel free to extend it, because if we can, then it means that it can describe a larger space-time. But really we can't, because of this odd behavior at L equals R, singular behavior. We shouldn't really think that there is there are two sides of this L equals R described by this metric. You can use it to describe one or the other side, not both together. So that, yeah.
Is this still a solution of deSitter Einstein equation with the cosmological constant?
Yeah, I think it is. And I think that's because that manipulation to check that it's a solution isn't going to care about the sign of about the size of R relative to L. Okay, so you define a coordinate u, which is t minus a half log t L plus R upon L minus R. Some discussions of deSitter set L equals 1 from the beginning. That's very disturbing, because then you get all kind of dimensionally inconsistent things. But more than that, you lose the physics of what is really happening. Like this, for example, again makes sense when R is less than L, because then it's a log of something real. And we can see that this is going to be a bit of a trick, because we make this change and afterwards we'll do something with that. So far we are still in the region R less than L, which is what we inherited from our embedding space time. And if we differentiate this, we immediately find du is dt minus, this of course is by construction, and this factor was found by integrating this. So now Note one amusing, useful thing is that if R is very small and it can be neglected in comparison with L, then this is dt minus dr, which is the familiar null coordinate we have already studied. And in these coordinates, the static patch metric becomes L squared minus R squared du squared minus 2L du dr plus the last term, nothing happens to it. And the basic thing is we've got rid of any L squared minus R squared factors in the denominator. And also, so now you see that this is defined for R less than L because it was just derived using some manipulations, all of which were done for R less than L, so that's fine. It's also defined at R equals L. This term goes away, but this term is there. It just simply says that du and dr are both null at R equals L. And it also survives for R greater than L, in which case this changes sign. Okay, and so this is well defined for all positive R. So at R less than L, R equals L and R greater than L. And now we really have one metric and we can say that, well, it's not like a physical process, but we can say that we can imagine being at R less than L and continuing to R equals L or R greater than L, and nothing will go wrong. Okay, and the killing vector here is d by du. Again, it's only one of them, but this one is time like for R less than L, it's null here and it's space like here. And so we can actually understand that the vector which was time like actually bends and becomes null on this point. And of course, I still didn't use that H word, but this is the horizon. So R equals L is a horizon. There's a rigorous definition of horizon and we'll spend a lot of the course talking about it. But for now, you can think of it as a locus where the causality structure changes, and certainly it's a clear change when something goes from being time-like to space to null to space-like. That's a change in the structure of the causal structure, so that's a horizon. Right now, there's no implication whether one can go through it or in which direction, but we'll find that also in a few minutes. Didn't there used to be a clock in this room? Oh, they painted the room. That's what they've done, and removed the clock. Okay, fine. Good. Any questions about static coordinates? Okay, then we move on to the next set of coordinates. We have quite a few actually to cover in this case. It's quite entertaining. Again, I would emphasize that you should, to the extent you have time to work on these things, you should play with the various coordinates and ask questions about them. I won't have addressed all of those questions. So the next set of coordinates are called conformal coordinates. And the idea here, actually the idea is in a way partly to get a Penrose diagram out of it. We want coordinates where the space-time is simple and finite with a factor outside. Then we drop that factor and go to an unphysical space-time and keep working with this thing inside the brackets. So our metric was, so we start with a global one. So it's going to be global. So the Penrose diagram should be global, because we want to cover everything that the deSitter space-time could have, and then we can ask, when we get the diagram, we can ask, oh, in static coordinates, what part of the Penrose diagram is covered, and we can see it explicitly. and then we can try to find reasons for that. So here we have this metric, the global coordinate metric. Now if we want to get, oh, there's an L squared outside. If we want to get a factor outside, so what we want is to write this as something times minus dt squared plus d omega d minus 1 squared. Because the thing inside is very simple, and it's a direct product of a sphere and a time. It's actually S d minus 1 cross r, and it's a sphere of a fixed size. So can we do this? Well, to do this, we just need to make a change of coordinates only of time. So let's think that this t is a function of t tilde. And then in that case, this original metric becomes set t equals t of t tilde. Then we have L squared minus dt by d tilde, dt by d tilde, dt by dt tilde. Sorry, it's a tongue twister unexpectedly. So this is kind of this is what we want. It's not what we have already. So let me rub it out. We will come back in the next line. And here we have cos squared t, where t is a function of t tilde, d omega squared. And now we'll get what we want if these two things are the same. So require dt by dt tilde equals cos t, which you can integrate. Now it's very easy for people to say you can integrate, and I integrated it once upon a time a few months ago, and I wrote a solution in my notes, but today before the lecture I wasn't able to reproduce it. So I'm leaving it to you as an exercise. What I verified is that I'm not the only one who has that solution. I don't know what I'm doing wrong, but I'm throwing this with a little caution. I think it has to be right, but I don't know, it's very tiring to find identities between. So the idea is that the hyperbolic function is replaced by a trigonometric function of another variable. So there, I forgot to mention there are two references on deSitter spacetimes. One is Hartmann, which you can look up the reference, and one is Spradlin et al., which are basically much longer. These are some Lesuche lecture notes of Strominger probably, and this is Hartmann's own course lecture notes. It's quite brief. So these are references. Spradlin certainly has this as the solution, and with this you can see that 1 over cos squared of t tilde comes out, and so we get the metric t squared is L squared over cos squared of t tilde minus dt tilde squared plus d omega d minus 1 squared. Now, of crucial importance is that t was one of the global coordinates, and so t was running from minus to plus infinity. So now it's our job to figure out what t tilde runs over. It has to follow from this, and we find that with this change of variables, minus pi by 2 is less than t tilde is less than pi by 2. So it's a finite region of time. We shouldn't be surprised because, of course, this is there in front and this can go to 0. So the ds squared can be as large as we want, but we are going to make this into our unphysical metric. And so removing the conformal factor, And when we do that, I'll try to use this practice of putting a tilde because this is not the true space-time interval and we should never confuse that it is. So the metric has become very simple. We simply dropped all that. And this has a name which is too grand a name for a very trivial thing. It's called Einstein static universe. Obviously in that context it had some reason to be named, but it's just, this is a sphere, this is time, and it's a unit sphere, so that's that. Now, as you know, it's not easy to draw a sphere, a higher dimensional sphere. The best we can usually do is to draw a one of its directions and ask you to imagine the others. So a nice thing one does for this is to write this as this plus. Now any sphere can be written as sine squared theta. Sorry. So the metric on any sphere can be written in this way: d theta squared plus sine squared theta d of the one lower sphere. This is actually how you can construct the metric on any sphere, starting from the metric on a circle, which is very trivial, and then go to a two sphere, and then you just keep adding new coordinates and putting a sine theta there. And it requires a little more stuff, but basically this is the way to do it. Now we have two coordinates, t tilde and theta, and that will allow us to draw a Penrose diagram. But first let's remember that when we do this, then 0 is less than theta is less than pi. Let's also try to understand the geometry of writing this sphere in terms of this thing. Let's just draw a little diagram before we get to the Penrose diagram, just the theta diagram. Theta is valued on a interval. I should have drawn it vertically, but in this course, vertical is always reserved for time evolution. But theta varies from 0 to pi on a sphere, and basically it's north pole and south pole. And there's a condition, there's a convention. Yeah, I use this is north pole, this is south pole. Hartmann uses the opposite. Now, what is the size of the d-2 sphere as theta varies? Okay, the radius is sine theta. That's 0 here and it's 0 here. So you can say that here there's a d-2 sphere sitting over this interval, but it's almost invisible. By the time we get here, it's bigger. We get here, it's still bigger. We get to the midpoint, theta is pi by 2, it's the biggest it's going to get. After that, it starts shrinking again. And here it's back to 0. This is the d-2 sphere. Oh, this S was south pole. Let me call it south. Now, you can sort of imagine how this works. In fact, you can imagine a very concrete example. Imagine that D was 3. Okay, so you have an interval and you have a circle. SD-2 is S1, a circle. So you have an interval and there's a circle here which starts growing like this and then collapsing there. What circles are these? They have a name in latitude. Latitude if you look sideways. Yeah, these are the latitudes. This is exactly the way we construct the two sphere of the Earth in terms of latitudes. There is no latitude direction which is phi or azimuthal angle. That's azimuthal angle, no? I never remember oh, that's azimuthal. Then this is called something else. I keep forgetting.
No,
that is azimuthal. Yeah, I think that is. Yeah. This is
one is polar.
Polar. Good. So theta is polar, and this is so it's the azimuthal angle which actually doesn't exist on the north and south pole. And then the cross section slicing the Earth this way just grows until the equator. This is the equator, and then it shrinks. And the same picture holds, just increasing the dimension as you like. is very important. So it's not, I'm not introducing this fact for just for entertainment. It's actually very, very important in our interpretation of the Penrose diagram we are going to find. And as we said, theta is between 0 and pi. Okay. So let's draw the diagram. So here's theta, here's t tilde. Here's 0, t tilde starts at minus pi by 2 and ends at plus pi by 2. Theta starts at 0 and ends at pi. And so we have a square. Well, my squares are not very square, but okay. Hopefully this is more square. There it is. Now let's analyze it a little bit. First of all, this is the easy one. What is this region? This is future infinity in time. But we can see from this that this is very much a space-like line. So it is future time-like infinity. It's not null. In fact, in a way you can think that the geometry is not different from Minkowski for this unphysical space-time, but the boundaries are totally different. Minkowski was in between a diamond and this is between a square, and that changes everything. So this is called Stri plus and this is called Stri minus, and this is the far past and the far future, and every particle should start here and try to go there. Good. So the time-like, so we have time-like, past and future asymptotic boundaries. So the horizontal boundaries are done. What about the vertical ones? What are they? Theta equals 0 and theta equals pi. They are the ends of the diagram, but are they some kind of boundary on space, or what is it? It's just a failure of the coordinate system, because it's, as I said already, this is the North Pole and this is the South Pole. So it's not a physical, it's just, this is actually the whole thing is a point. So we draw it as a dotted line. I think I used this convention also in Minkowski, where the zero line was also, we had this kind of wedge shaped thing, and this was again a coordinate singularity, just the one of spherical polar coordinates. So now what you're supposed to imagine is that if I cut this at a fixed time, that's the spatial slice. The spatial slice, theta goes from 0 to pi, but while it does, there is this phenomenon happening. So over this whole line, exactly that thing is happening. There is a sphere, d minus 2 sphere, which is growing, shrinking. And so the whole composite thing, this line times the sphere sitting over it, is the one higher dimensional sphere, sd minus 1 of our unphysical metric. Okay, so everything makes sense. And that's all the labeling we need for this. Okay, now we have to show somewhere, and I seem to have shown it and lost it also, that null rays travel at 45 degrees. Okay, this is only true if they are not propagating on the d minus 2 sphere. So this how often happens. In Minkowski, this direction was the radial direction r, now it's an angular direction. But we often talked about things moving in r and t. So by assumption, we said that whatever is that internal sphere, they are not changing that value of the coordinate. And that's what happens when something goes radially. Here also, we are allowed to consider processes where theta and t tilde change, but the remaining coordinates of this sd minus 2 don't change. And for those, we can make statements. Why have I not got the formula telling me that these things go at 45? There was some tedious calculation, but I don't seem to find it. Okay, I'll just have to state it without proof, leave it as an exercise. So, null rays travel at 45 degrees. Remember, this was one of the great motivations for Penrose diagrams, that we can understand causality. If they don't move on SD minus 2. If they do move on SD minus 2, then it effectively makes them appear slower in just the t theta space, so they will be at a higher angle. Okay. Now, the interesting thing in this diagram is, okay, if I am a time-like observer, it's pretty clear that I'll go like that, or I might bend. I have to calculate what I'll do, but I'll start somewhere on here and I'll end somewhere on here. But for a null ray, something interesting happens, which is that the future light cone of a point only covers half of this square. So let's see, for example, this point. Its future light cone is like that. Okay, this is the future light cone. There's nothing beyond that, but it's only half of the square. This is the future light cone. It follows from my previous statement about null rays going at 45. What about past light cone? If I was here, my past light cone covers this region.
Future light cone, you made the future light cone by starting at theta equals to pi.
Yes.
So, can't you?
I could do it at theta equals 0, then it would be this. Still half the square.
It can be this one also, right?
Yeah, it can be. Those are, yeah, because you see, we have chosen coordinates which have this behavior at 0 and pi. So it's convenient to consider 0 and pi. If I consider any other point, I have to do a little more work to see what is exactly happening. So because I'll hit this coordinate singularity first. But 0 and pi give us correct answers, and so which is the future light cone is not so much the question, but that it's half of the. So first of all, future light cone is half of the whole thing, whole space-time, and that means that a particle starting here can never hope to influence anything happening in this bottom left half. So that is the statement of a horizon, and also that any event here could not have been influenced. Let's say the event. Let's see, what do we want to say? The event here could not have been influenced by anything which happened in this part. Okay. If we want to consider the region, I'm just drawing this again a little better. Where the point theta equals pi can influence the region and the region can influence something at that point, then I'll be restricted to this part. This is in the future light cone of this point and in the past light cone of that point. It's the intersection of the two. And what is this? Actually, it's an easy exercise, but I'm lazy to do it for you on the board, so I'll leave it for you as an exercise. It's exactly the static patch. So the static coordinates, what you have to do is you have to look at the static coordinates, then go through our construction. Remember, the static coordinates restrict to a wedge in the embedding space. Now you can then go from the embedding space through the this change to the global coordinates, then this change of this conformal factor to go to the conformal coordinates, and you should land on this wedge. But again, with a different convention, it could have been the left wedge. There's no invariant choice, it's just a convention. Okay. So this statement, so let's write the statement. deSitter has an observer dependent. In fact, you can see that because it depends on who the observer is, where the horizon is. And it's called a cosmological horizon. And it is going to share some features of black holes, but clearly it's not a black hole, it's just a space-time. Okay, but it's like another example in GR of how causality doesn't end up being what you think it is. Like you would think it's obvious that I can influence events in the future and so on. In Minkowski, that is certainly true. Light ray will be able to influence the whole of space-time if it starts far enough in the past. But here you can start as early as you like and you'll never reach some places. Now you can say that, well, actually we are not surprised because in the original coordinates, the global coordinates, it's an expanding space-time. So you can sort of have an intuitive feel that you're trying to reach some place in space-time, but space-time is expanding, so you'll never reach there. It'll by the time you try to get there, it'll have expanded away from you, something like that. So that's the general idea behind such a horizon. Okay, then the last thing to cover, and we are almost done anyway, and that will take only 2 minutes, is the one more set of coordinates we have, which are called planar coordinates. Planar or Poincaré coordinates. So for these, they carry both names. What you do is this also covers half of the global space-time, but it is not half. This time it is half. In the static patch it was like a quarter. It was a quadrant. So this will cover x0 plus xd greater than 0. So it actually covers this region. Now we are not in the Penrose diagram. This is the infinite space-time. And what we do to find these is to single out. So we single out x0 and xd, and we are left with the other xa's, which are d minus 1 in number. And we set these equal to an expansion factor et times the new coordinate xa, and we put in the deSitter radius here. So this is like an expanding version of this, and this will behave like some kind of flat d minus 1 dimensional space, and that flat space, not a sphere now, it will be an expanding flat space. If you think in the beginning, the global coordinates had a exponential expansion given by cos squared of t multiplying a sphere, so there was an expanding sphere. But here it's going to be an expanding flat space. You might wonder what that means, but of course it means that any pair of points in that flat space are going to fly apart from each other. So let's complete the derivation. So with this, we have minus x0 squared plus xd squared plus L squared e to the 2p xa has to be equal to L squared. To solve this is the constraint. We are still at the constraint, and then we have to work out the metric. To solve this, we have L sine hyperbolic t plus L by 2 xa e to the t, and xd is L cos hyperbolic t minus L by 2 xa e to the t. And now you can see what I predicted, that x0 plus xd will be positive. If you add these terms cancel, and these terms add up to give e to the t. In a way, these coordinates are cleverly chosen so that e to the t plays a role. Exponential expansion as against cosh. Cosh has an exponentially expanding part and also some other part which is decreasing in either direction. This one is, or another way to say it is, this is expanding unilaterally only in the future. It won't be expanding in the past, while cosh expands both in the future and past. Okay, and in this coordinates you get a remarkable simplification. ds squared is just equal to minus d, so L squared minus dt squared plus e to the 2t dxa squared. So this is what I said. This is a plane dxa, d minus 1 dimensional. The whole plane is exponentially expanding only to the future. You can of course flip t to minus t and you will get it expanding to the past, but you can only have one or the other. So this is expanding right from beginning of time, it's continually expanding. It's not like the other picture we had of deSitter. And there are a couple of little changes of variables people do, like if you say t prime is e to the t, then this will become dt prime over t prime, and so this will become L squared into minus dt prime squared upon t prime squared plus t prime squared dxa squared. And there's also, if I define, what do I call it? I don't want to call it u. I don't have another name. T hat is 1 by t prime, let's say. Then this becomes L squared. So this stays the same. So you get t hat squared here minus dt squared plus dxa. In this description, you can think of it as a entire Minkowski spacetime that's unit, that sort of the whole thing is expanding or contracting, both the time and space together. In this description, only the space is expanding.
What
Okay.
patch of the original Penrose diagram this corresponds to?
Yeah. When you say original Penrose diagram, the Penrose diagram.
The Penrose, yeah.
Yeah, I think it's the same top right half. I believe it's the top right half. So it should be, I'll verify this, but I think it's this. You can check. Huh?
Can we see that it's always increasing, the flat space time is?
Well, this is, this Penrose diagram is not going to give you correct information about size of anything. The whole point of it was that we took a fictitious metric by scaling out a factor. That factor is crucial in determining sizes. It's not crucial in determining angles. So it only gives reliable information about angles. But for example, when a part of space-time is cut out, like in this case, then I think it reliably gives you, because it's again about the null rays, because it preserves the direction of null rays. But whether you can see more from the Penrose diagram, I don't know, but it would be surprising because it's not the real metric. It's not based on a genuine metric.
Also, when you describe this, the fact that these observers sees this cosmological horizon, that statement, is that also true if you start from any other point?
It is. It's just that it becomes harder to describe, because if you do that, you'll hit the north or south pole.
Yeah.
That's a coordinate singularity. So then you just need to figure out what happens when it hits the north or south pole. So that's why it's most convenient to describe from the corners where it's not going to hit the other pole except at the final point.
Also, one more thing. So these null rays can also be less than 45 degrees, as you said. If they
That means more vertical. Yeah,
if they move along SD.
that's right. Correct. Any more questions? Okay.
The increasing nature of expanding nature of universe can be seen from as we increase t.
Yeah.
The physical metric, we took the conformal factor 1 by cos
Right,
theta.
exactly.
So that factor will keep on increasing.
Yeah, because cos goes from minus pi by 2 to pi by 2. So as we go to either end, it will keep increasing. That's correct.